The F-22 Raptor represents the most expensive bet ever placed on air superiority, a $67 billion wager that the United States would need to dominate airspace against an enemy that, by the time production ended, barely existed. Here's the uncomfortable arithmetic. 195 aircraft delivered at roughly $350 million each when you fold in development costs. And for that price, you got a fighter so classified that your closest allies couldn't buy it, so complex that mission-capable rates hovered around 50%, and so exquisitely optimized for air-to-air combat that bolting on proper ground attack capability became a decade-long software nightmare. The Raptor wasn't designed to be practical. It was designed to be utterly untouchable in a dogfight, to see everything while being seen by nothing, to arrive before anyone knew it was coming, and leave before wreckage stopped tumbling. In that singular, breathtakingly narrow mission, it succeeded beyond any previous benchmark in aviation history. Whether that success justified the cost depends entirely on whether you believe the next major war will be won or lost in the first 30 minutes of air combat, because that's the window the F-22 was built to own. The story begins in the early 1980s, when the Air Force looked at emerging Soviet aircraft like the MiG-29 and Su-27 and realized the F-15, magnificent as it was, wouldn't maintain superiority forever. The Advanced Tactical Fighter program launched in 1981 with requirements that read like science fiction: Supercruise without afterburners, stealth, advanced avionics integration, short takeoff distance, and agility that would embarrass anything currently flying. Two teams emerged, Lockheed with the YF-22 and Northrop with the YF-23, and both prototype aircraft were genuinely extraordinary. Northrop's bird was faster, stealthier, and arguably more elegant. Lockheed's was more agile, and crucially, came from a team the Air Force trusted more for program management after Northrop's troubles with the B-2. The YF-22 won in 1991, just as the Soviet Union was collapsing, and what had been designed to counter a massive threat suddenly became a very expensive solution looking for a problem that was rapidly disappearing. But the Pentagon doesn't cancel programs easily, especially ones this far along, and there were reasonable arguments for continuing. Stealth technology worked spectacularly in Desert Storm. China was beginning its long military modernization. Russia might rebuild. Technology overmatch had become American doctrine, and the Raptor represented overmatch taken to its logical extreme. So development continued through the 1990s. Delays mounted, costs ballooned, and the aircraft that emerged in 2005 was simultaneously a technical masterpiece and a strategic orphan. It had no peer competitor. It had no export market. It had marginal relevance to the counterinsurgency wars actually being fought. And it was so sophisticated that keeping it operational consumed resources, like no fighter before it. The F-22's design philosophy can be summarized as uncompromising. Where other aircraft balance stealth against payload or agility against range, the Raptor's designers pursued maximum performance in every regime that mattered for air superiority and accepted brutal compromises everywhere else. The result is an aircraft with capabilities that still, 2 decades later, no other fighter fully matches, and limitations so severe that it's functionally unusable for half the missions modern air forces actually fly. If detailed technical breakdowns of aviation design and the strategic decisions that shape them interest you, subscribe. I've got more of these analyses coming, and there are plenty of aircraft worth examining this closely. Start with the airframe itself, a study in geometry dictated by radar physics. Every surface, every angle, every edge exists to scatter electromagnetic energy away from the source. The fuselage is a flattened diamond in cross-section, blending seamlessly into wings with a 42-degree leading-edge sweep. The twin vertical stabilizers cant outward at 27 degrees, keeping them outside the aircraft's primary radar reflection lobes. All weapons carriage is internal, tucked into 3 bays, a large central bay for 6 AIM 120 AMRAAMs, or 2 AMRAAMs plus 2 1,000-pound JDAMs, and 2 side bays for 1 AIM-9 Sidewinder each. This creates clean external lines with 0 pylons, 0 bumps, 0 radar returns from missiles hanging in the slipstream, and exactly 0 ability to carry the kind of heavy ground attack loadouts that modern wars often demand without destroying the stealth profile. The Air Force eventually certified external carriage for ferry missions or low-threat environments, but the moment you hang bombs on the wings, you've turned a $350 million stealth fighter into an extremely expensive F-15 with worse payload capacity. The structure itself uses a mixture of materials chosen for strength, weight, and radar transparency. Titanium forms roughly 40% of the structure by weight, clustered around high-stress areas and engine bays where temperatures spike. Aluminum alloys handle less demanding loads. Composite materials, primarily bismuth imide and carbon fiber, make up about a quarter of the airframe, used extensively in skins and non-structural fairings where you need specific electromagnetic properties. Every composite panel is manufactured to tolerances measured in thousandths of an inch because stealth requirements don't allow for sloppy gaps or misaligned edges. This precision makes production slow and repairs expensive. Damage a composite panel on an F-16, you might patch it or fabricate a replacement in days. Damage one on a Raptor, you're looking at weeks and specialized facilities because the panel's radar signature matters as much as its structural function. Then there's the skin coating, the classified radar-absorbent material that turns bare metal into something approaching invisible. Early RAM coatings were fragile, prone to bubbling in rain, degrading in sunlight, and requiring laborious reapplication after every few sorties. The F-117 and B-2 suffered similar issues, but the Raptor was supposed to be an operational fighter, not a hangar queen. Lockheed eventually developed more durable coatings, but even the improved versions require climate-controlled hangars, careful maintenance, and regular inspection. Stealth isn't a permanent feature, it's a condition you maintain through constant, expensive effort. This is why mission-capable rates stayed stubbornly low, not because the aircraft broke frequently, but because keeping it mission-ready demanded so much preparation. A deployed Raptor wasn't just a fighter, it was a logistics tale of specialized equipment, trained maintainers, and environmental controls. Propulsion comes from 2 Pratt & Whitney F-119 turbofans, each delivering 35,000 pounds of thrust with afterburner, and here the Raptor genuinely breaks new ground. The F-119 was the first operational engine designed for sustained supercruise, the ability to exceed Mach 1 without lighting the afterburners. Supercruise matters because afterburners are fuel-devouring, infrared blazing beacons announcing your presence to every sensor within 100 miles. The Raptor can cruise at Mach 1.8 in military power, sipping fuel at rates that let it cover ground faster than subsonic fighters while maintaining a far smaller infrared signature. The engine achieves this through a high bypass ratio design optimized for efficiency at supersonic speeds, advanced turbine materials that tolerate extreme temperatures, and sophisticated engine control software that constantly adjusts airflow for maximum performance. Each engine weighs about 3,900 pounds, generates a thrust-to-weight ratio exceeding 7.1, and costs roughly $10 million. They're also relatively reliable by fighter engine standards, with longer intervals between overhauls than earlier high-performance turbofans. The inlet design deserves its own discussion because it illustrates the Raptor's obsessive approach to stealth. Conventional inlets point straight back at the compressor face, creating a massive radar return from all those spinning metal blades. The F-22's inlets curve in an S-duct, blocking direct line of sight to the engine while maintaining smooth airflow across the speed envelope. The duct walls are coated with RAM, the geometry is optimized to scatter radar energy, and the entire assembly is canted to present minimal frontal cross-section. This works beautifully for stealth, but creates challenges for engine performance, especially at high angles of attack where airflow into the inlet becomes turbulent. The flight control system compensates, adjusting inlet ramps and bleed doors to maintain stable airflow, but it's yet another system that has to work perfectly for the aircraft to deliver advertised performance. Thrust vectoring adds another layer of complexity and capability. Each engine nozzle can deflect up and down 20 degrees, controlled by the flight control computers to enhance pitch authority during high alpha maneuvering. Combined with the Raptor's aerodynamic design and a thrust-to-weight ratio exceeding 1.1 at combat weight, this enables maneuvers that seem to violate physics, controlled flight at 70-degree angle of attack, violent pitch transitions, post-stall gyrations that leave conventional fighters floundering. Pilots describe the sensation as unnatural, the aircraft responding to control inputs that should cause a departure, but instead producing precise, stable movement. The downside is maintenance complexity. Thrust vectoring nozzles add actuators, seals, control linkages, and failure modes. They increase inspection requirements and parts count. For air-to-air combat at visual range, they're remarkable. For the beyond visual range missile exchanges that dominate modern air combat doctrine, they're an expensive luxury. Aerodynamically, the Raptor balances stealth geometry against flight performance with mixed results. The trapezoidal wing has a fairly high aspect ratio for a fighter, optimized more for efficient cruise than instantaneous turn rate. Wing loading at a typical combat weight runs around 375 kilon per square meter, higher than dedicated dogfighters like the F-16, but lower than heavy strike aircraft. The leading edge sweep and planform are dictated by stealth, not lift distribution, which means the wing isn't optimized for subsonic agility. Leading edge flaps adjust to improve lift at lower speeds, but the Raptor doesn't outturn an F-16 in a slow-speed scissors. It doesn't need to, because it fights differently. The design assumes you'll use superior situational awareness, Supercruise, and stealth to dictate engagement terms. You don't dogfight, you shoot from beyond visual range and leave. When merge happens anyway, thrust vectoring and brute engine power compensate for aerodynamic limitations. The flight control system is quadruplex fly-by-wire, 4 independent computing channels cross-checking constantly because the Raptor is fundamentally unstable without computer intervention. The aerodynamic center sits behind the center of gravity, making the aircraft dynamically unstable in pitch. It wants to tumble, and only constant computer corrections keep it stable. This instability is intentional, trading natural stability for responsiveness. Control surface movements happen in milliseconds, faster than any human could react, enabling the aggressive maneuvering that thrust vectoring amplifies. The system is transparent to the pilot under normal conditions, but it also means that losing flight control computers turns the Raptor into an unflyable brick. Triple or quadruple redundancy mitigates this risk, but it can't eliminate it entirely. Now we reach the part that truly separates the F-22 from every fighter before it, the integrated avionics suite. The AN/APG-77 radar is an active electronically scanned array, no moving parts, just a fixed panel of roughly 2,000 transmit-receive modules that can steer the beam electronically across a 100-degree field of view. Scan rates are measured in microseconds. The radar can track multiple targets simultaneously while maintaining low probability of intercept, shaping its emissions to minimize the chance that enemy receivers detect they're being painted. Detection range against fighter-sized targets exceeds 200 kilometers, and the system can burn through jamming with focused beams that older mechanically scanned radars couldn't match. It's not just a radar, it's a multifunction sensor that handles air-to-air tracking, ground mapping, electronic warfare, and data link communication. Later upgrades expanded synthetic aperture radar modes for higher resolution ground imaging, turning the Raptor into a more capable strike platform, but those capabilities came years after initial deployment. The radar integrates with the AN/R56 infrared and ultraviolet missile launch detection system, which watches for the characteristic plume signature of inbound missiles, and the AN/ALR-94 passive radar warning receiver, a system so sensitive it can detect enemy radars at ranges exceeding the radar's own detection range. The ALR-94 uses more than 30 antennas distributed across the airframe, providing complete spherical coverage and accurate angle of arrival data. In practice, this means a Raptor crew can detect an Su-35's radar emissions from 400 kilometers away, long before the Su-35's radar has any chance of seeing the Raptor's stealth profile. You can track threats passively, build a firing solution without emitting, and engage without ever lighting up your own radar. This passive detection advantage, more than raw stealth, defines how the F-22 fights. All these sensors feed into the common integrated processor, essentially the aircraft's brain, fusing data from radar, infrared, electronic warfare, and data link into a single coherent tactical picture displayed on the cockpit screens. Sensor fusion sounds like marketing speak until you've seen it work. Instead of the pilot mentally combining data from 6 different instruments, each showing raw sensor output, the system does the correlation and presents threats, friendlies, and unknowns on one display with confidence levels and threat priorities. This reduces pilot workload dramatically, letting one person handle situational awareness tasks that previously required a 2-seat crew. The downside, again, is complexity. Software integration became a nightmare, with upgrades taking years to certify because changing one element rippled through the entire system. Early Raptors had limited air-to-ground capability, not because the hardware couldn't handle it, but because the software architecture didn't prioritize it, and retrofitting those modes meant rewriting core fusion logic. Cockpit design follows the F-16 philosophy of panoramic visibility, with a bubble canopy offering nearly 360-degree views. The pilot sits high, with excellent sightlines over the nose and acceptable views aft despite the aircraft's bulk. Primary flight instruments are gone, replaced by 4-color multifunction displays and a wide field of view head-up display. The HOTAS, hands on throttle and stick, puts every critical function within thumb reach, letting pilots manage sensors, weapons, and countermeasures without looking down. The ejection seat is a McDonnell Douglas Aces Tachkund, the same proven system used in F-15s and F-16s, rated for 0-0 ejection. Pilot feedback on ergonomics is generally positive, though the cockpit runs hot during ground operations in warm climates because environmental systems prioritize cooling avionics over crew comfort. Performance numbers tell part of the story, though many remain classified. Maximum speed exceeds Mach 2.25 at altitude, though operationally you rarely push that hard because it burns fuel catastrophically and risks damaging the stealth coating. Supercruise speed sits around Mach 1.8, sustainable for extended periods without afterburner. Service ceiling is above 60,000 feet, giving the Raptor an altitude advantage over most opponents. Combat radius varies wildly depending on mission profile, but figure roughly 750 kilometers on internal fuel for a typical air superiority mission with Supercruise segments and combat maneuvering reserves. That's not terrible, but it's not outstanding either. An F-15C carries more fuel and can extend range with external tanks, an option the Raptor sacrifices for stealth. Ferry range with external tanks reaches about 3,000 kilometers, but again, you've negated stealth by hanging fuel pods on the wings. Operationally, the F-22 entered service in 2005 and immediately became the most carefully guarded asset in the Air Force inventory. Export was forbidden by federal law, preventing sales even to close allies like Japan and Australia who desperately wanted it. The official reason was protecting classified stealth and avionics technology. The practical result was killing any chance of international cost sharing that might have made continued production economically viable. Production ended in 2011 at 195 aircraft, well short of the 750 originally planned, because unit costs had spiraled beyond sustainability, and the aircraft's relevance to ongoing wars was marginal at best. Combat deployments have been limited and carefully managed. The Raptor's first combat action came in 2014 over Syria, striking ISIS targets, using a $350 million air superiority fighter to bomb technicals and buildings because it happened to be available and the Air Force wanted to justify its existence. Later operations against Syrian air defenses made more sense, exploiting stealth to operate in contested airspace. But even there, the missions could have been flown by older aircraft with standoff weapons at lower risk and far lower cost. The Raptor's real combat test, the peer conflict scenario it was designed for, hasn't happened. We have red flag exercises where F-22s achieved ludicrous kill ratios against simulated opponents, and we have pilot testimony about the psychological impact of fighting an enemy you cannot see or track. But we don't have extended combat data against an actual near-peer threat operating with full sensor integration and modern doctrine. What we do have is operational data about maintainability, and it's sobering. Mission-capable rates, the percentage of the fleet ready to fly at any given moment, consistently run below 60%, sometimes dipping into the 40s. Each flight hour requires roughly 34 maintenance hours, nearly double the F-16's ratio. The stealth coating, environmental control systems, advanced avionics, and thrust vectoring nozzles all demand constant attention. Deployed operations require significant support infrastructure. The Raptor isn't an aircraft you scatter across austere forward bases. It's a thoroughbred that needs specific conditions to perform. This limits flexibility and increases operational costs in ways that aren't captured by simple per-hour flight costs. Given its combat record, the costs involved, and the missions modern air forces actually fly, was the strategic decision to prioritize absolute air superiority over versatility the right call? Or should the focus have been on greater numbers of more flexible platforms? Let me know what you think in the comments. Upastu. Comparisons with contemporaries illuminate the Raptor's position. Against the F-35, the Raptor is faster, more agile, and stealthier in the frontal aspect, but the F-35 has better all-aspect stealth, more versatile ground attack capability, sensor fusion refined over an additional decade of development, and international sales driving down unit costs through economies of scale. The F-35 is the fighter you can actually afford to build in quantity, deploy globally, and use for the messy multi-role missions that constitute real-world air operations. The Raptor is the fighter you wheel out when air superiority against a capable opponent is genuinely in question. Against the Su-57, the Russian answer to fifth-generation requirements, the Raptor has maturity, proven systems, and likely a significant stealth advantage, but the Su-57 exists in tiny numbers and hasn't demonstrated the integrated avionics performance that the Raptor pioneered. Against the J-20, China's heavyweight stealth fighter, we're comparing the Raptor's known capabilities against an aircraft shrouded in operational security, though the J-20's larger size suggests emphasis on range and payload over dogfighting agility. The more relevant comparison might be with the F-15, the aircraft the Raptor was meant to replace. The F-15C remains in frontline service, still a formidable air superiority fighter, and it does so at a fraction of the Raptor's operating cost with far better maintainability. The Eagle carries more missiles, operates from rougher fields, and has actual combat kills numbering over 100 across multiple conflicts. It lacks stealth, lacks Supercruise, lacks sensor fusion, but it's proven, reliable, and you can afford to have enough of them to matter. The Raptor's advantages are real and significant, but they come at costs that make mass deployment impossible. You get 195 Raptors, or you get 750 upgraded F-15s. Which wins the war? Modernization efforts focus on software, sensors, and weapons integration because the airframe itself is essentially fixed. Avionics upgrades have added better synthetic aperture radar modes, improved electronic warfare capabilities, and integration with newer weapons like the AIM-120D and AIM-9X. Data link improvements let Raptors share information with F-35s and other coalition assets, though integrating the Raptor into broader network architectures has been challenging because it was designed before modern data link standards matured. Helmet-mounted displays, standard on the F-35, haven't been retrofitted to the Raptor, leaving pilots dependent on head-up display and screen-based targeting. The Air Force is pursuing further upgrades to extend service life into the 2040s, but there are limits to what you can retrofit. The basic sensor architecture, the cooling capacity for avionics, the internal weapons bay dimensions, these are baked into the design and can't be fundamentally altered without rebuilding the aircraft. The elephant in the room is cost versus capability in an era of precision missiles and integrated air defenses. Modern surface-to-air systems like the S-400 can engage targets at ranges exceeding 250 kilometers. Stealth reduces detection range but doesn't eliminate it, especially against low-frequency radars that can detect stealth aircraft at longer ranges even if they can't generate a targeting quality track. The future battlefield might belong to loyal wingman drones, expendable unmanned platforms that absorb risk, while crewed fighters quarterback from standoff distances. In that paradigm, do you need a $350 million manned fighter with Supercruise and thrust vectoring? Or do you need a cheaper sensor shooter platform controlling a swarm of attritable drones? The Raptor was designed for a different war, one where manned fighters meet in high-altitude knife fights, and the side with better sensors, stealth, and maneuverability wins decisively. That war may never come, replaced instead by missile exchanges beyond visual range, drone saturation attacks, and integrated kill chains where individual platform performance matters less than network effectiveness. Pilot perspectives on the Raptor are overwhelmingly positive regarding performance and almost universally frustrated regarding operational limitations. Flying a Raptor in red flag exercises, dominating the opposition with impunity, is apparently intoxicating. The situational awareness, the confidence that you see threats before they see you, the knowledge that your missile can reach them before theirs can reach you, it changes how you think about air combat. But pilots also acknowledge the aircraft's limitations, the restricted payload, the maintenance demands, the inability to operate from austere fields, the frustration of having extraordinary capability and limited opportunity to use it meaningfully. There's also the reality that fewer than 200 aircraft means fewer pilots get to fly them. And those who do know they're operating a sunset platform with no replacement on the horizon. The Next Generation Air Dominance program promises a sixth-generation successor, but it's years away and may embrace radically different concepts that reduce reliance on manned platforms entirely. The F-22's legacy is complicated. Technologically, it validated concepts that defined fifth-generation fighter requirements: stealth, sensor fusion, Supercruise, advanced avionics integration. The lessons learned, both successes and failures, directly informed the F-35 program and influenced designs worldwide. Every nation pursuing advanced fighters now treats stealth and sensor fusion as baseline requirements, a shift the Raptor pioneered. Operationally, it demonstrated both the extraordinary capability overmatch can provide and the crippling costs that come with it. Strategically, it stands as a cautionary tale about designing exquisite platforms for threats that evolve differently than predicted. The Soviet Union collapsed. China rose. Counterinsurgency consumed 2 decades. Peer conflict remained theoretical. The Raptor arrived magnificently prepared for a war that didn't happen, too expensive to risk in wars that did, and too specialized to adapt easily when requirements shifted. If you found this analysis useful, a like helps more people discover these deep dives into aviation and strategy. Thanks for watching. In the end, the F-22 Raptor is exactly what it was designed to be: an air superiority fighter with no peer in its specific domain, achieved through uncompromising engineering, eye-watering costs, and acceptance of severe limitations everywhere outside that domain. It's a masterpiece of aerospace engineering that may never face the combat scenario that would justify its existence: a $67 billion insurance policy against a threat that proved less dire than anticipated. Whether that makes it a success or a cautionary tale depends on what happens next. If near-peer conflict erupts and air superiority proves decisive, the Raptor will be vindicated. If warfare continues evolving toward distributed operations, missile exchanges, and unmanned systems, it will stand as a monument to the limits of exquisite platforms in an era demanding mass and flexibility. Either way, we won't build another fighter like it. The costs are too high, the strategic environment too uncertain, and the lessons too clear. The Raptor is both the apex and the end of a particular vision of air combat, the last of the manned dog fighters, engineered to perfection for a mission the future may not require.